All matter is made up of atoms or molecules. For example, water. Each water molecule consists of 2 hydrogen atoms and 1 oxygen atom. An oxygen atom has 8 electrons traveling around the nucleus. The nucleus consists of elementary particles called nucleons, of which there are 2 kinds. Protons, positively charged particles, and neutrons, which have no charge at all. The oxygen nucleus normally contains 8 nucleons of each type. Since positive and negative charges balance each other, the whole atom is electrically neutral. Now, what force holds the nucleons together? Let us consider a single example, hydrogen. In approximately every 7,000 hydrogen atoms, 1 atom is of a particular type. In addition to the proton, its nucleus contains a neutron. For this reason, it is called a heavy hydrogen nucleus. Consider a proton and a neutron some distance apart. The particles cannot exert electrical forces on one another because the neutron has no charge. Therefore, they follow their own paths without affecting each other. It is only if they come very close together that suddenly an attractive force is set up. This is the so-called nuclear force, the exact behavior of which is still unknown. Suppose a normal hydrogen nucleus approaches a heavy one. As is well known, bodies with like charges repel each other. Thus, to bring them together, an external force must be applied. At small distances, the repulsive force is tremendous. But again, if the nuclei come very close together, the nuclear force suddenly starts acting. This force is so great that it easily overcomes the repulsive force of the protons. The new particle thus formed is the nucleus of a special type of helium, which occurs very rarely, in only 1 atom of about 800,000. A normal helium nucleus has 2 neutrons. Summing up, there are 2 types of helium nuclei, the light nuclide and the normal nuclide, and 2 types of hydrogen nuclei, the normal and the heavy nuclide. The heavy hydrogen nuclide is called deuterium. There is also a 3rd type of hydrogen which contains 2 neutrons and occurs in extremely small quantities. It is called tritium. But what of oxygen? We have already seen the structure of a normal oxygen atom. But 1 atom in about 3,000 contains 9 neutrons. And 1 atom in about 500 has as many as 10 neutrons. All these atoms contain 8 protons and 8 electrons. Therefore, oxygen is given the atomic number 8. It is this number which determines the chemical behavior. The difference between the 3 oxygen nuclides is in the total number of nucleons, that is, 16, or 17, or 18. The three nuclides are called isotopes of oxygen: O16, O17, and O18. These isotopes are chemically identical. In each of the two isotopes of helium are 2 protons. Consequently, they both have the atomic number 2. The 3 hydrogen isotopes have the atomic number 1. Now we can arrange the different nuclides according to the number of protons and neutrons they contain. The simplest nuclides are the 3 isotopes of hydrogen. Each has 1 proton and 0, 1, or 2 neutrons respectively, so that the total number of nucleons is either 1, 2, or 3. The next nuclides in the table are the 2 isotopes of helium, with 2 protons each and either 1 or 2 neutrons. The place where the single neutron belongs is beneath hydrogen 2. Next to helium is lithium, and so on. Oxygen, as we have seen, has 3 isotopes. Fluorine, the next element, has only 1. Continuing, we come to heavier elements. Chromium, for example, has the atomic number 24 and 4 isotopes. The table ends with uranium, which has the atomic number 92. There are 3 isotopes of uranium, of which U-238 occurs most frequently. The U-238 nucleus contains 146 neutrons and 92 protons. Now the nuclides can be divided into 2 groups. The larger group, shown in black, contains the so-called stable nuclides. The smaller group, shown colored, contains the unstable or radioactive nuclides. There are also a great many other radioactive nuclides which can be made artificially. To understand what is meant by the words stable and radioactive, we must take a closer look at the elementary particles which make up the atom. The electron and the proton have equal electric charges of opposite sign. The neutron has no charge. Another important property of a particle is its mass. The mass of the electron is very small. We will give it the symbol small m. The proton is much heavier, large M. The neutron is heavier than the proton, but the difference is only 2.5 times the mass of the electron. Now let us imagine a free neutron, one which is not bound inside a nucleus. The neutron splits spontaneously into a proton and an electron. It is important to study this reaction carefully. The charges of a proton and an electron are equal and opposite, matching the 0 charge of the neutron. But what about mass? Since we have only 1 electron, we can see that 1.5 electron masses have disappeared. In fact, this mass has been converted into energy, the kinetic energy of the electron. This is a demonstration of Einstein's law that mass and energy have an equivalence and can be converted into each other according to this formula, relating energy, mass, and the velocity of light. Disintegration of a neutron can take place in several nuclei. Let us consider tritium. One of the neutrons is transformed into two particles, a proton, which stays in the nucleus, and an electron, which flies off. The energy set free in this reaction is used partly to overcome the force of repulsion between the protons, whilst the remainder is given to the electron in the form of kinetic energy. Comparing the two states, it is seen that the nucleus at the left has one proton and is therefore an isotope of hydrogen. The nucleus on the right has two protons and thus cannot be a hydrogen isotope. In fact, it is the light helium isotope, helium-3. Both of these reactions, that of tritium and that of the neutron itself, may be shown by means of equations similar to those for chemical reactions. For historical reasons, electrons emitted in this way are called beta particles. These kinds of nuclear reactions are called electron decays or beta decays. The beta decay of the neutron and the tritium nuclide can also be shown in the table. The neutron decays to hydrogen and tritium to light helium. Generally, a beta decay is represented by one step to the left and one step upwards, because one neutron is lost and in its place one proton is gained. The next nuclide showing beta decay is beryllium-10. Its decay product is boron-10. There are isotopes of carbon, potassium, rubidium, indium, and also of some very heavy nuclides. All these nuclides belong to the small group of unstable or radioactive nuclides. It may now be clear why a distinction was made between the two groups. As its name implies, a radioactive nuclide decays spontaneously, whereas a stable nuclide can be changed only by external forces. A substance being radioactive does not mean that its decay is instantaneous. In any large number of neutrons, some will decay immediately, while others will take longer. Decay takes place at a speed determined by the half-life of the substance. The half-life for neutrons is 12 minutes. This means that after 12 minutes, 1/2 of the neutrons will have decayed. And after another 12 minutes, 1/2 of the remaining neutrons, and so on. Thus, radioactivity gradually decreases with time. Every radioactive nuclide has its own specific half-life, varying from a fraction of a second to billions and billions of years. It may well be asked why some nuclides are stable and others are not. To understand this, let us take any nucleus and see what forces are at work. First, there is the nuclear force, holding the nucleons together. This force is opposed by the repulsive forces of the protons. Therefore, at first sight, it would seem that a nucleus would be most stable if it contained only neutrons. Such a nucleus does not exist in nature, but if it did, it is easy to see what would happen. One neutron after another would decay by beta emission. Simultaneously, the repulsive forces of the protons would grow, making further beta decays more and more difficult. Finally, an equilibrium would be reached in which the protons already present prevent the creation of new ones. In the table, a nuclide of neutrons only would be located on the baseline. After successive beta decays, a stable position would be reached. Now all equilibrium positions, shown in black, form the narrow band occupied by the stable nuclides. This band separates two regions, one in which there are too many protons, and the other in which there are too many neutrons. If a nuclide is located in the latter region, one or more of the neutrons will show beta decay, as we have seen with the radioactive nuclides already discussed. The other region contains only 3 nuclides. One of these 3 is an isotope of beryllium. This isotope has an excess of 1 proton. This proton can be transformed into a neutron with the aid of an electron which is captured from the inner electron shell of the atom, or the K shell. This process is called electron capture, or K capture. In the case of beryllium, this K capture is followed by the emission of an electromagnetic wave called a gamma ray. In the table, K capture is indicated by 1 step to the right and 1 step downwards, because 1 neutron is gained at the expense of 1 proton. Summing up again, there is a narrow band which contains stable nuclides and which separates 2 regions containing radioactive nuclides. In one of these regions, neutrons predominate and beta decays occur. In the other region, there is an excess of protons, which gives rise to K capture. These processes are accompanied by gamma emission on many, but not all occasions. With heavy nuclides, for example, uranium-238, a third type of radioactivity occurs. This uranium isotope can emit a helium nucleus, followed by the emission of a gamma ray. Since the nucleus loses 2 protons and 2 neutrons, this is represented in the table by 2 steps to the left and 2 steps downwards. Helium nuclei are called alpha particles. The exact mechanism of emission of alpha particles is not fully understood, since the behavior of the nuclear force is still obscure. However, it appears that the nuclear force builds up to some form of saturation, so there might be a cluster of 2 protons and 2 neutrons wandering around the nucleus, and influenced by the forces of repulsion of the other protons. These repulsive forces can be so great, especially in heavy nuclei, that the alpha unit is ejected. Inspection of the table shows that the decay product of uranium-238 is thorium-234. But this nuclide is also radioactive. 2 successive beta decays will take place, giving uranium-234, which will in turn emit an alpha particle, and so on. Until lead-206 is formed, which is no longer radioactive. A sequence of radioactive nuclides, like the one just discussed, is called a radioactive chain. There are 3 of these chains. They start with uranium-238, uranium-235, and thorium-232. It may well be asked how it is that radioactive nuclides exist at all, since they tend to decay towards a stable state. Many radioactive nuclides were formed at a time when cosmic conditions differed greatly from today. Due to their enormous half-lives, some of them have survived in the Earth's crust. Others are being produced from the decay chains of uranium and thorium. And today, the light radioactive isotopes are being created continuously in the upper layers of the atmosphere, where the nuclei are broken up by an endless stream of cosmic rays.